The goal of our project is to design a robot that can move and take measurements at designated locations on surfaces of low-gravity bodies, like, for example, asteroids and comets. Small bodies are becoming a key target for space exploration for a variety of reasons. They're seen as a stepping stone toward the human exploration of the solar system. Their understanding could prevent potentially catastrophic impacts with our planet. Their characterization could shed light on the origin evolution of the solar system and even on the origin of life on our planet. Now, moving on small bodies is hard for a variety of reasons. First, you have to get there. And two of the most important missions to small bodies, like, for example, Hayabusa and Rosetta, have failed or had mishaps in deploying a rover. Once you are there, there is a difficulty of remaining attached. Since gravity is very low, you tend to bounce around and flip. So essentially, wheels do not work well anymore. And the environment are extremely challenging. So here, for example, you can see a picture take from Rosetta. You can see how irregular the terrain is, how dusty the terrain is. So our strategy to design a robot that can move controllably on small bodies is to leverage internal actuation. In a nutshell, the idea is to have internal flywheels that are mounted within the enclosure on the robot. And by accelerating or decelerating the flywheel, we can transfer the angular momentum to the platform, and in turn, we can give rise to either hopping or tumbling. Now, my student Ben Hockman is going to give a demo about the platform.
So angular momentum is built up internally, and then a mechanical brake causes it to flip over. So that's just a quick demo, and we can also do different types of maneuvers. I'll show you a pointing maneuver. So right now what's happening is a flywheel on the bottom is spinning, so the angular momentum is pointing up. So what this can do is help to change orientation. So there's a lot of different maneuvers that we've been exploring with these flywheels. But the big question is, we've demonstrated this on Earth, and all the equations have told us that it should work in a microgravity environment, but we really haven't been able to test until this past summer in a really relevant environment. So we took this prototype and another prototype down to Houston and flew on the Vomit Comet for 200 parabolas. And if you guys aren't familiar with that, it provides about 20-second windows of relative weightlessness. So in each of these 20 seconds, we were able to test a maneuver. Okay, so we have various materials that we can test on. So this is actually a garnet sand that we put into a little container. And interestingly, it behaves very different in microgravity. So the gravity levels here are about 10 to the minus 2 G. So a couple orders of magnitude lower than Earth. Okay, another material that we've played around with is a comet regolith simulant that's been developed at JPL. And we've broken it up to show that indeed these rovers can robustly hop on very uneven surfaces. One of the questions that kept coming up is what happens if it gets stuck in the regolith? If it were to come into contact with the surface and bury itself, could it indeed escape? We did indeed test that with this aggressive spin maneuver, and it turns out the geometry of the body and when it's buried provides an upward torque, so it can kind of screwdriver itself out of the regolith, which is pretty spectacular to watch.
Overall, our hope is to one day have our robot standing maybe on Phobos and running around and tumbling and hopping.